Okay, so here on the third of probably four, I don't know, videos here on the endocrine system, we're going to talk a little bit about how hormones maybe interact a little bit in some other ways. So prior to this, right, we talked about how we have releasing hormones and entropic hormones that are responsible for the release of hormones from other organs and things like that. But they also are going to have interactions sometimes at the target cell itself. And that's really where we're going to begin here. We're going to kind of branch off into stress responses and things like that. But there we go. So for that to work here, what we're going to talk about generally speaking is modulation is the idea, right? And there are three forms of modulation or interactions at the target cell that are worth worrying about. These are synergism, permissiveness, and antagonism. And the role of antagonism, oh, sorry, I'll pull up the video. There we go. Hormone modulation here. So synergism, permissiveness, antagonism. And with synergism, this is when we've got two hormones that both do the same kind of thing. They both have the same kind of interaction with the target cell. And so when they both arrive at the target cell, they have a larger response. The sum is greater than the individual parts, basically. The opposite of this, of course, is antagonism, right? Where we have one that stimulates, one that inhibits. And so again, what we're going to do is we're going to kind of add the effects together. And so if it's a stronger stimulant and a weaker inhibitor, we'll have a decreased stimulating effect. If it's a stronger inhibitor and a weaker stimulant, we'll have a decreased inhibition effect. But again, we'll be modulating or altering the effect depending on what the hormones are. And of course, permissiveness, this one here in the middle, is kind of a weird one, where we require the presence of another hormone to do the job. Okay, so if we have only hormone A, nothing will happen. But if hormone A and hormone B are both present, then activity can happen. That's what permissiveness is. So let's look at an example of that. We can. There we go. So here we've got a couple of different hormones here: insulin, glucagon, epinephrine. Insulin and glucagon are antagonists. Okay, insulin causes the storage of excess glucose in the blood. Glucagon causes the release of it from storage. Okay, so insulin, then we would expect to find that it would lower blood glucose levels. And so when we look at just insulin, right, our control, we see that as we add it over time, right, we have a decreasing amount of sugar in the blood, right? Our serum glucose levels decline. When we have both insulin and glucagon, okay, so here we've got two antagonists. Okay, glucagon is going to modulate the effect of insulin. Insulin is still going to lower serum glucose, right? It's going to lower blood sugar, but less than it does just by itself. Epinephrine also, it's not a primary function, but epinephrine also plays a role in the release of or the inhibition of insulin, right? Again, we have an antagonistic relationship here. And so insulin and epinephrine, we have, again, a diminished effect of insulin. Insulin still has this lowering effect on blood glucose, but less than it would be by itself. So the other fun part about this is that not only are epinephrine and insulin and glucagon and insulin both antagonistic relationships, epinephrine and glucagon are actually synergistic. And so when we have all three of them together, the combined effects of glucagon and epinephrine actually outweigh the effects of insulin. And so we have a net increase in blood glucose. Again, all these sorts of different interactions that we might expect can have very different effects. And so if we want to have different effects on, say, serum glucose levels, we can play around with how much insulin, glucagon, epinephrine, all these things that we release. Okay, so now as promised, the ultimate fun expression of all of this stuff here, the sort of the mammalian stress response. This is going to involve both the sympathetic nervous system and the HPA axis in slightly different ways. So the HPA axis, which is going to be this side over here, okay, we have release of this the CRH hormone here, which then acts on the, it's a releasing hormone on the anterior pituitary, okay? And the effect here is that we're going to release adrenocorticotropic hormone, right? We're going to go and we're going to release glucocorticoids from the adrenal cortex, okay? And that net effect there, so again, the stress here being our primary stimulant, that net effect here is going to have all of these delayed physiological effects, okay? So what we're talking about here is a long-term stress response, okay? The hormonal or endocrine side of this is a long-term response. What does this mean? It means we break down proteins, okay? And they have a glut of amino acids in the body. And we use those amino acids to turn into glucose, all right? Gluconeogenesis is the production of glucose from pyruvic acid or any other set of parts that we can build it up, okay? So the liver is going to be taking these amino acids and turning them into glucose, and so we have elevated glucose levels. In the same time here that we're doing this, we're also breaking down fats, okay, into individual fatty acids and glycerol, which then, of course, we also turn into more glucose, okay? We inhibit gonadotropins, we inhibit growth hormone, we inhibit thyroid stimulating hormone. So growth shuts down, okay, anabolism, building shuts down, catabolism begins. We begin breaking down the building blocks of your body, which is not great, right? And of course, the other part of this here is that they are also going to act opposite to insulin, right? We're not going to store glucose, we're going to use it. And the idea here is that we're under some kind of, at least biologically anyway, the idea is that we're under some sort of nutritional stress, that we need to have as much glucose available for the central nervous system, which can't run on anything else, to continue to function, right? Now, in terms of the short-term stress response, this is going to be here the sympathetic nervous system, right? And you might notice a couple of our good buddies here, norepinephrine and epinephrine, as a result of this. And the stress response here causes sympathetic activation, right? Which has all of these fun things that we associate with being stressed out, right? Elevated heart rate, elevated rest rate, your digestion falls off a cliff, okay? And again, like what's happening over here, we have elevated blood sugar, basically. And these two actually kind of knock on each other. They are a positive loop, okay? Norepinephrine here increases activity in the hypothalamus. The CRH here, this releasing hormone from the hypothalamus, in turn, enhances a lot of the sympathetic activity, right? And so they do feedback on one another. And of course, there are always, because this involves regions of the brain, there are always psychological effects that come into this. You're alert, if you've ever been stressed out and trying to sleep, right? You're aware of this. But you also, because this is a emotionally stressful time, you're more likely to form memories here as well. So it's a big, long, old, delightful event. One of the other big concerns here, of course, is the effect on the immune response. Okay, the stress response here has a pretty profound negative effect on the immune response. And the reason why, if we look back here kind of at the immune system cells itself, whatever cells they end up having to be, there's a variety of different cells here. But these immune cells, amongst their products, are these things called cytokines. And cytokines, you might have heard the term cytokine now because it's in the news because of things like cytokine storms, which are extremely dangerous secondary immune system responses to illness. But cytokines themselves are not dangerous in and of themselves. They just are molecules that modulate the activity of other cells. That's all they are. Okay. In this particular case, right, our cytokines are going to stimulate the hypothalamus here into releasing more of this CRH, right, which in turn has this whole feedback loop here with glucocorticoids, so on and so forth. The reason that this is dangerous for your immune system, the reason that stress responses are dangerous for your immune system, is that glucocorticoids, right, in addition to being a negative feedback loop, like we talked about before with the Hpa axis, they also have a negative or a depressant effect on immune system activity, okay, because of this cytokine connection. And so stress response actually dials down the effectiveness of your immune system altogether. So it can be pretty scary and pretty dangerous kind of knock-on effect for a lot of this stuff. Okay, into the less horrifying things, if we go back to insulin and glucagon, the release of these two hormones under normal circumstances is tied predominantly to mealtime, okay? And the idea here is that we like to maintain homeostasis, right? We don't want blood sugar too high, we don't want blood sugar too low. When we are eating, okay, we're dumping a lot of sugar into our blood, which would cause blood sugar to spike, potentially. We don't want that. And when we're between meals, when we're in a period of fasting, we're going to use that sugar, right? We might run into a situation where blood sugar drops. We also don't want that, okay? And so we have this net effect here of having to deal with these ebbs and flows, or we could release a couple of different hormones that can kind of squash those peaks a little bit, right? It's like what we're trying to do with COVID right now, right? We're trying to flatten the curve. This is what insulin and glucagon are doing for us, right? In terms of our blood glucose levels, we're trying to flatten those curves out a little bit. So what we might expect then is that in the period immediately following a meal, we would see insulin spike, right? And then as we kind of move into a fasting period, okay, insulin levels will decline, glucagon levels will raise so that we can, again, start releasing some of that stored glucose and not fall off a cliff. One of the tricky parts about all this is that your body responds, at least with insulin anyway, responds to a very heavily protein-rich meal in the same way that it does to a carb-rich meal. Okay, so what we're seeing here, the heavily proteinous meal, so you had a steak and nothing else, right? You don't increase blood glucose levels at all because you didn't have any glucose in your body or in your meal, but you still release a bunch of insulin. So the danger with a protein-only meal is that you can very quickly run into a low blood sugar situation. Okay, now your body is going to respond to that, right? It is going to figure out, oh crap, we don't have any sugar, and release a bunch of glucagon. But, okay, my speaker shut off. But in kind of response to that, we will start dumping out glucose. Of course, this is going to use up our stored glucose. Going to use up our stored glucose supply, but it's better than dying, right? Generally speaking. Okay. One of the other things that we've talked about, it kind of danced around a little bit here and I haven't really spent a lot of time with, is this sort of relationship between blood volume, blood pressure, kidneys, vasopressin, aldosterone, things that we've talked about a little bit. And the very basic part of it, the simplest way that I can explain this, and we'll talk more about kidneys later on, but basically the idea here is that your kidney makes a lot of decisions, right? It filters the volume of your blood several times a day. And then one of the decisions it has to make is how much water do we end up putting into our urine? Okay, now the way that we do that ultimately, right, is by deciding how much sodium do we put in the urine and how much sodium do we return to the blood. And the reason that we care about that, right, is because of osmosis. The more sodium we put into the urine, the more greater the osmotic pressure, and the more water will leave the blood and enter the urine. Okay, or if we put more sodium back into the blood, water will leave the urine and go back into the blood. Right, water will follow that sodium. So, right, a couple of different hormones here, depending on where they're sort of rooted at. Vasopressin, right, or aldosterone, one from the pituitary, one from the adrenal cortex. They're both going to have the same net effect, right, which is fluid retention. Less water in the urine, more in the blood. So a raise in blood volume, which leads to a rise in blood pressure. You think about it like a balloon, right? The more air you put in the balloon, the more pressure there is inside of it. The same thing with your blood. The more blood you've got in your circulatory system, the more pressure resides within that. Now, it's a little more complicated than that, right? Again, depending on which kind of hormone we're talking about. Here with vasopressin, what we're doing is we are putting in more of these special water pores. As we talked before, when we talked about osmosis, before we talked about one of the ideas is water can just kind of bully its way through the cell membrane, right? But we can also have specialized pores for the transmission of water across a membrane, these aquaporins. Vasopressin produces more of these aquaporins, puts more of them in the cell membrane, and so making it easier for water to flow from one to the other, right, back out of the kidney and into the blood. Whereas aldosterone, right, our net effect here is through a big long chain of different hormones, but the reabsorption of sodium. Okay, we're going to make the blood saltier, which is going to cause more water to flow back into it. Now, renin-angiotensin, this whole big long nightmare, is important. Okay, we're going to simplify it a little bit as much as we possibly can. Okay, but we are going to need to kind of go through it here a little bit. What we'll talk about that, I guess, when we talk about the kidney, I guess is where I'm ultimately going with that. Another big balance issue, okay, particularly with the blood that we talk about, is with calcium. We don't want to be hypercalcemic, which is too much calcium. We don't want to be hypocalcemic, which is too low, for different reasons. Hypocalcemia without calcium, your nervous system doesn't work. Your skeletal muscles don't work. Right? We talked about, at least with the nervous system, we talked about the fact that a big part of the release of neurotransmitter was calcium. And if we don't have it, it don't work. So if we have low calcium, we need to get it from somewhere. Where we get it from is from bone. And so a hormone called parathyroid hormone. So here's the thyroid gland right here. This is the posterior view of the thyroid gland. So the trachea here. These little bean-shaped nodules on the back of the thyroid here, these are the parathyroid glands. And they produce parathyroid hormone, which ultimately, here's our old friend cytokine again. Ultimately, what this does is it pulls calcium out of your bones and puts it into your blood. That's mostly what we end up doing. Now, that's not ideal for your bones, right? So we need to be able to put that back. We do so using sex hormones, vitamin D, all that good stuff. If calcium is too high, on the other hand, that's also bad. We get kidney stones. Kidney stones can block outgoing tubules, and you can die from kidney stone, believe it or not. So we don't want that either. It also can depress immune system function. It can, or not immune system, can depress nervous system function. It can depress muscles, all the function of muscles. Bad stuff. So we need to make sure that we're not adding more calcium than we need to. Okay, and that's a hormone from the thyroid gland called calcitonin. And what calcitonin does is it basically takes these cells, right, that were stimulated by parathyroid hormone to remove calcium. It basically stops them. So we stop pulling calcium out of your bones. Okay, and eventually we're going to use the calcium that's in your blood. We're going to use that. We're going to bring that level back down through normal use. We can also put it back into your bones, again, through the action of sex hormones. But again, here with calcitonin, the idea is not to reverse the activity, but simply to stop the activity of parathyroid hormone. Okay, so that's the end of part 3. In part 4, we'll finish this thing off. We'll talk about some fun things, some more interesting things, and then we'll transition into sexual reproduction. If I can stop the video, that'll be the next thing.